Hello and welcome to another Chemistry 221 live stream. This is brought to you by Portland State University. I'm going to throw a few links for Portland State in the chat there. These are links to the Learning Center's Facebook, Instagram, and their webpage as well. I'm also going to throw a link to a YouTube channel that has all of the videos I've been making this summer term on it. So definitely check those out and review for your final and stuff like that using those videos and textbooks and all the other resources you have available to you there. Today we're going to be talking about a little bit about electron configurations. We're going to talk about electronegativity, Vesper geometries, electron geometries, and molecular geometries, as well as some of the Lewis dot structures and a little bit of dipole moments and polarity as well. So we got a lot to cover today. This is going to be the last one of this series. You guys have a final on Friday, so best of luck with that. Definitely review for the final as best you can. And if you're following on to Chemistry 222 for this next part of the summer term, I'll see you here. We're going to have the same videos at the same times as well. So let's get started today. On this first question here, we're going to write the electron configuration for monoatomic ions formed with all of these following elements. And this first one, we're looking at chlorine. When we look at the ion that's formed from chlorine, it's going to be just a -1 charge, right? So for the electron configuration, we want to find its standard configuration. In this case, we're going to add one extra electron to it. So if we use the core notation to it, which speeds things up a little bit, we can go to our periodic table, and I'm actually going to slide around here. This is the one I'm looking for. So we can see that chlorine sits down here on the periodic table. You can see that. Maybe I'll make it red. Might make it stick out a little bit more. It's a group 17 atom. It's a halogen. And if we use the core, it's going to have a neon core to it. So we just go to the next noble gas one period up, and we call that the core. And then basically it has the core electrons, or everything that's in neon, plus all these extra electrons to make chlorine. So we can write this then as a neon core. And notice also chlorine is on period 3. It's the third period, the third row down. So we can start out just with the 3s2, 3p5. That's normally what chlorine would be. Since it's negatively charged, it's going to have one extra electron in there. That one extra electron is going to turn that 5, oops, a big eraser, turn that 5 into a 6. And then it will actually have the same basic electron configuration as argon. So jumping back to my periodic table, you see argon is actually one up from that. It's going to have the same electron configuration as argon there because it's added one more electron to it. Jumping on to part B, this is going to be sodium. Sodium is going to be a positive charged ion. So it gets that +1. It does that because it's a group 1 element. It's one of your alkali metals. And so it's going to lose one electron when it ionizes, leaving it as a +1. So it's going to be right here on your periodic table. Again, a group 3, or sorry, period 3, group 1 atom. And it's also going to have that neon core that we talk about. So normal sodium would have that neon core plus a 3s, so just one electron in the 3s shell or subshell. But in this case, it lost that. It's ionized. So it doesn't actually have that. So really, it has the same as a neon core. There's no real difference to that. We could also write that kind of in the notation of a helium core, which is He. That would then be 2s2, 2p6, which really brings you all the way back up to neon as well. Part C, magnesium. That would be a 2+, because magnesium That's one of your alkali metals there. So that's that second column there. They're always going to ionize as a +2. It's going to lose both of its 3s electrons. So that's the third period still. So it's going to actually be the same as sodium plus with just a neon core. And we could write that also, same idea, He 2s2 2p6. And I forgot to change my color, so I'm going to do that now for continuity. Part D is calcium. Now calcium, looking at our periodic table, we can see it's also going to be that group 2 metal. So it's going to ionize as a +2, but it's now down on period 4. So period 4 is down there. So when it ionizes +2, it gets the core not of neon, but of argon. Argon's that noble gas 1 row up from where calcium was on the periodic table. So we can write that as an argon core, and it would be normally 2s2 because it has two. I'm sorry. We're on the 4s now. 4s2. So normally we're at that 4s level, but it's lost both of those to become 2+, so it loses those. It's really got that same as the argon core, which is really a neon core, 3s2, 3p6. Notice I didn't put any 3d electrons in there because that 3d electrons don't really come into play until we look at the fourth period here. So when we're talking about the argon core, they don't have any 3d electrons in there. We'll clean this up a little bit, starting to get messy. And we'll go ahead and jump over to part E. E is potassium. Potassium has a +1 charge to it when it ionizes because it is a group 1 metal. That group 1 metal, when it ionizes, becomes the same basically as our argon core up above. So this is going to also produce an argon core, which would also be a neon core, 3s2, 3p6. But argon core is good enough. We could write the entire thing out and call it a 1s2, 2s2, 2p6, 3s2, 3p6, but that becomes really hard to, or not really hard, just really long to say and tedious to say them for all of these different things, which is why they kind of came up with this core notation. Saves a lot of time. For part F, F is bromine. So bromine ionizes with a minus charge. Bromine we can see is one of our halogens. Bromine is over here, number 35 on the periodic table. It's going to be a group 17. So bromine, since it ionizes as a -1, it gets an extra electron and shoots up. So it's actually going to end up being the same as our krypton. Have the same configuration. So we can say, we can write it out with an argon core. So that's going to be actually the one that's before it. This is argon. And then this is in period 4. So when we write this out, this is going to be a 3s2. Sorry, period 4. Knew that sounded weird. 4s2, 3d10, 4p, and then it would normally be 4p5, but we're adding one extra electron to make it ionized, 4p6, which is the same as saying it's krypton. So the strontium, part G. So looking over and finding strontium on there, that's going to be a group 2 metal here in period 5. So, and that gets ionized since it's on group 2. These are all going to be 2+. That whole group 2 category. So that's going to be a 2+ as well. So normal strontium would be, since on 5 it's going to have a krypton core. So Kr. We could say then 5s2. My 5s and s's look very similar, so let's make it clear, 5s2. That's what normal strontium would be, but those get eliminated because we lose those electrons during ionization. It becomes the same electron configuration as just that krypton core. We could also write that kind of with an argon core. That's Ar core, 4s2, 3d10, 4p6. That's the same idea as just how a krypton core there. The last one we have is fluoride. This is going to be part H. Fluoride gets ionized as a -1 charge because it's up here, group 17, row 2, top of the halogens, the most electronegative, which we'll talk about in just a little bit. So it gets that -1 charge. Really, whenever anything ionizes, it's trying to get as close as possible it can be to a noble gas, which is why oxygen ionizes at -2, fluoride ionizes at -1, sulfur is again -2 because it's right here below oxygen. This one is nitrogen is more of a -3. Carbon kind of can go both ways. It could go -4, it could go +4. It really likes to have those 4 bonds. That's why there's a lot of carbon things, because you could bond to a lot of different stuff. So fluoride, I digress. Fluoride really has a helium core to it, and then it would have a 2s2, 2p5 normally, but it's going to go up to 6. But that's really the same as saying an argon core. I'm sorry, a neon core. Whew. I almost forgot about neon. So one thing we can notice here is there's a lot of similarities between these. We notice that these two here both had an argon core when it came down to it. The same electron configuration. And so did this one up here. The chloride, the calcium ions, the potassium ions, they all had the same electron configurations with them. They had different protons in the middle, different neutrons floating around in there. That's what the protons make them the different atom altogether. The electron configuration, however, can be the same for all of them. The same is true for sodium plus and magnesium 2 plus, as well as this fluoride down here. I'm going to hop over this other one and connect that up to there. Those three also have that same core configuration, and so do these two in the middle here. The bromide and the strontium, they have the same electron configuration when they're ionized. So ions can oftentimes share the same electron configurations with those based on these. The only difference is the number of protons and possibly neutrons in the nucleus. So that's my run through on electron configurations. Your textbook has some pretty good notes on different types of periodic tables, how the different elements usually ionize. Notice that all of group 17 is going to be -1, most of 16 is -2, most of 15 is -3, and carbon's always -4. Same with group 1 minus hydrogen is always +1, group 2 is always +2. Those transition metals can be a little different in there, but certain ones like silver, Ag, is always going to be +1. Zinc is always going to be +2. Aluminum is always +3. Those are ones you're going to see pretty often in there. So definitely use some of the resources. These are just some names of the different groups there. Also talking about the different subshells that you have there, the 2s, the 3s, the 4s. Basically all your s electrons are over here on the left, groups 1 and 2. Your transition metals are going to be all your d block. Your 13 through 17 is going to be basically all your 2p. I'm sorry, 13 through 18 is all your p electrons, your p block that's there, and that tells you where all of the different electrons are going to be. Your anthonides and lanthanides are all down here as your F block electrons. You don't see those very often until you get down to row 6 or 7 on the periodic table. And then there's a nice table that actually tells you exactly what everything's going to be when it's neutrally charged. Once you ionize it, you can add or subtract electrons based on that, basically jumping to the next one or jumping back from it. So let's go on to polarity. So polarity is when you have this idea of electronegativity. Every atom in there has what we call electronegativity. How happy it is to be negatively charged. And the most negatively charged atoms we have on there is going to be fluorine. And this is kind of a trend of electronegativity on the graph. And we can see that as atoms move farther to the right, their electronegativity grows. So fluoride up here, this is your most electronegative. It has an electronegativity of 4. And everything kind of spreads out from there. So the farther it goes this way, we have a decrease in electronegativity. The farther away from fluoride you get, you're going to get a decrease. So if you move farther to the left on the periodic table, the same row, you can see fluoride at 4 goes down to oxygen at 3.5, nitrogen at 3, carbon at 2.5, boron at 2, and so on. But also, if you go farther down on the periodic table, you can see chlorine is 3 electronegative, bromine is 2.8, and iodine is 2.5. So the farther down you get on the periodic table, the less electronegative it is. The farther to the left of the periodic table, the less electronegative it is. The most electronegative is always fluoride, and usually if it's in the same row, you can just count the same steps away, and that's going to be a greater electronegativity than if you were to go down. You can see oxygen's more electronegative than chloride, nitrogen is more electronegative than bromide, iodide and carbon are kind of the same in there, and when you go diagonal, you end up, it's like going a few away. It's even more so. You get a little bit of both effects. So you see 2.5 is a lot less than 3.5 and 3, or even 2.8 and 3. So the farther away you get from fluoride, the more electronegative you're going to get. And we can then use that electronegativity to start talking about polarity. So polarity is basically, we're looking at the relative strengths of that electronegative pull on the molecular bond. So in this case, we want to identify those polar bonds, and we can do that. But we want to see which one is more polar, is the idea. So we can do that by taking the numbers I just had on that graph between hydrogen and fluoride, and we subtract them from each other. I usually subtract the more electronegative for the other one, but you can also just take your absolute value. So in doing that, if we look at fluoride versus hydrogen, fluoride is 4, hydrogen is 2.1. So we can just really subtract that. That's going to be 4.0 minus 2.1. And we do that math, and we can see that's equal to 1.9. So that's the kind of the relative pull on the fluoride or the hydrogen in that bond. There's more electrons flowing towards the fluoride than the hydrogen. So we say that the hydrogen has a partial positive, the fluoride has a partial negative. That's the little delta symbol I drew in there, which looks kind of like that. If I draw it a little bit cleaner. We do the same for HCl. We're looking at chloride, which is 3.0. We can say that's 3.0 minus 2.1, which is equal to 0.9. So the more electronegative, the more polar between these is basically going to be the one with a larger difference in electronegativity. So we're going to have HF is going to be more polar than HCl. We can go on to NO or CO. So oxygen is 3.5, nitrogen is 3, and carbon is 2.5. So just looking at this, you can see that the difference between oxygen and nitrogen, let me zoom in, the difference between oxygen and nitrogen is going to be less than the difference between carbon and oxygen. So this bond here is going to be less polar than the bond formed by carbon and oxygen. And we can see that in the math. So oxygen was, now I forgot my numbers, 3.5, 3, and 2.5. So 3.5 minus 3.0 is equal to 0.5. And we can see that 3.5 minus 2.5 is equal to 1. So in this case, we can see that this guy is going to be more electronegative than NO is going to be. For SH versus OH, we see the H is the same. That's going to be 2.1. The S is either 2.5, get rid of all my scribbles, or 3.5. So oxygen being more electronegative than sulfur means that the bond between OH is going to be more polarized than the bond between sulfur and hydrogen. And we can see that here. So I'm just going to start circling OH is going to be a more polar bond. Looking at the difference between phosphorus chloride and sulfur chloride. That's phosphorus and sulfur is really the difference. And we're comparing that to chloride. So chloride is the most electronegative on, or in there, on that row, basically. And we can see that the difference between sulfur and chloride is going to be smaller than the difference between phosphorus and chloride. Excuse me. So that phosphorus chloride bond is going to be more polarized. And we can see that again in the math. 3.0 minus, what was it? 2.1. 2.1, that's equal to 0.9, and 2.5. 2.5 minus 2.1 is equal to 0.4. You can see this is a larger number. That's going to be more polarized. And we can do this with all of them. I'm going to skip down to this last one here. It's really the same idea. We're just subtracting those out. This one should be a really easy one because we have nitrogen bonded to nitrogen. That's dinitrogen, or elemental nitrogen we call it, because it's a diatomic gas. When CN is bonded together, we really have the electronegativity between carbon and nitrogen. And again, they're right next to each other on the periodic table. So you can see 3.0 minus 2.5 is going to be 0.5. But nitrogen bonded to nitrogen, that's going to be non-polar at all. So there's no polarity there, because nitrogen, when it bonds to nitrogen, we get a electronegativity of 0. We can say it's 3.0 minus 3.0, which is equal to 0. So that's how we distinguish between the different polarities of things, and we can figure out how, it's not polarities, distinguish between the electronegativities of the different atoms, and we can differentiate between the polar or non-polar, or even the gauge of polarity based on them. So now we're going to jump into some Lewis dot structures. Lewis dot structures, there's really one simple rule we want to follow. We want to make sure that we account for all the valence electrons and that everything has an octet rule, follows that octet rule. The octet rule states that the tendency of a main group of atoms to form enough bonds to obtain 8 valence electrons. So ultimately, in covalent bonds, we're sharing electrons between the different atoms, and we want to make sure that each atom has at least 8 electrons. Some of the atoms that are bigger can have more than 8 electrons, but really nothing besides a few exceptions wants less than. The exceptions being hydrogen, helium, bromine, and anything that's low on the periodic table. But we can say the tendency, let's write neat, of main group atoms to form enough bonds to obtain 8 valence electrons, to obtain 8 valence electrons. So we can try that out now on a few of these. I'm going to skip around a little bit and redact. H2 is pretty simple. It's not going to have that octet rule because you usually just have one atom between each of them. But with hydrogens, we see on part B, how I like to do it is I draw them out, H and Br, and then I figure out how many valence electrons am I working with here? How many total do I want to have? And looking at bromine, bromine is again jumping back to here, my favorite periodic table. Bromine's down here. on there, and that means it's a group 17. We can really just subtract 10 from there and say that it has 7 valence electrons in that one. And that's going to be 5 of the p electrons here, and then 2 from your s electrons. So that's a total of 7. So I would just draw those on there, but I can list them first. 7 electrons. And that's coming from bromine. And then there's 1 electron from hydrogen. So when they bond together, hydrogen's going to have 1. Bromine is going to have 7. I'm just drawing those on there. And then there's a bond between these. So they're going to share, those 2 electrons are going to create a bond, a covalent bond. So hydrogen is bonded to bromine. And then we can see on here, we want to verify, does bromine have its octet? Hydrogen doesn't need it. It's one of the exceptions. But bromine, it has 2 lone pairs there, 2 lone pairs there, 2 lone pairs there, and a bond. So it's happy. It's got 4 or 8 electrons totally floating in there. So that's our Lewis dot structure for HBr. For part C, PCl3, here we have chlorides. We have 3 of them surrounding a phosphorus. And when I look at this, I think, how many electrons does chloride need? I jump over here, chloride, which is right here, also a group 17. It's going to have 7 electrons in there. Yeah, okay. So I can go back and say, just counting 3 times 7 electrons from chlorides, plus, I'm going to add these together really to get my 8 total electrons, plus the phosphorus. So phosphorus has 5 electrons. It's in group 15 right here. So that's going to have 5 electrons to it. Phosphorus. So I can draw those on there now. I'm going to draw first the chlorides. Always draw the outer ones first. And we could also add up. That's going to be a total of 7 times 3 plus 5 is 26 electrons. So we can add electrons to make sure all of them, we count for all of the electrons, and everything has an octet rule. So I'm putting 6 around all the chlorides, and then I'll add 1 more for 7. And then I'm going to give phosphorus, it's 5. And I kind of made it so phosphorus and chloride, I know there's going to be a bond there between them, these little sigma bonds. So I gave one electron around phosphorus, pointed kind of towards that chloride, and then I can connect those up. And now I can see that chloride has its octet rule because it has 8 electrons that it's sharing. Mainly these two, these two, these two, and then a bond, and that's the same for all of these. And phosphorus also has its octet because it's sharing 2 with this bond, 2 with this bond, 2 here, and then it's got 2 extra lone pairs. We can jump down a little bit. Let's look at part E. So part E, I'm going to go down to here. It's H2CCH2. So they wrote that in a slightly different way. What they're really doing there is they're showing you kind of how these hydrogen and carbons are connected up together. So we know that there's 2 central carbons, and each one has 2 hydrogens on them based on that. So I can draw it out like this. I know each of those hydrogens are going to have 1. I know each carbon wants to have 4 because on the periodic table, it's in a group 14, and carbon always wants to have 4 bonds. So I can draw 2 of them on this side, 2 of them on that side, 2 of them on this side, 2 of them on that side. And I connect up my bonds. I know hydrogen and carbons want to bond together, and then the carbons have to have a bond together. But we have this extra electron floating on each of those carbons, and we notice that they don't have an octet. They have 3 sigma bonds each, and then 1 extra electron. So they don't have that 2 electrons they need to make that a pair, so they have that double bond in there. And now we have kind of this the Lewis dot structure of H2CCH2 in there. We can go on to part F. Well, let's go skip part F and go to part G. I don't want to spend all of our time on this one. So part G, this is H2CNH. So that's H2. So I can write it as HHCNH. Now we know carbon has 4 and hydrogen has 1, so I can draw those on there now. Put 1, 1, put the 4 for carbon, and 1 for hydrogen. Now we have to find out how many nitrogen has. Jumping to the periodic table, we see nitrogen is a group 15, which means it's going to have 5 valence electrons on there. Those 5 valence electrons, I'm going to put 3 of them pointing out towards the other ones, and then 2 more kind of floating up above. If we connect our dots now, we get this nice Lewis structure for it. And we can we can do a formal charge on this, which is what we're going to do on one of the next problems. I think a couple up. And we can see that it's all neutrally charged. Everything has its octet. Nitrogen has 3 bonds plus a lone pair. Carbon has 4 bonds, and hydrogen has 1 single bond with everything. We can do N2 now. Let's do I. So N2, that's a fun one because we really have 2 nitrogens floating there. And we just said each of them wants to have 5 electrons. So they have 5 valence electrons. So I can put a pair out here and a pair back there. But we know there needs to be an octet. We need to have 4 bonds, 8 electrons total. So really, we'll put the other 3 kind of in the middle. And then we can form a sigma bond and 2 pi bonds between those 2 nitrogens that are there. And we can see now that nitrogen really wants to have 3 bonds and a lone pair, because that satisfies its octet, and it's based on the fact that it has 5 valence electrons in its shell. So when it's bonded to another nitrogen, it's going to create this triple bond between them. Something similar is true with the next 2 as well. So if I do part J, that's a carbon and an oxygen bond. Now we've said that carbon wants to have its 4 bonds in there, but oxygen really wants to have 6 bonds in there. So I can even draw, it really has too many bonds for it. So what happens here is oxygen basically loans carbon a bond, so it can create this triple bond in there. And that triple bond then satisfies the octet rule for both of those charges. Where carbon, if we do a formal charge on here, just to jump ahead a little bit, carbon wants to have, or has 4 valence electrons in it, and then it has 2 lone pairs. So we subtract those 2 lone pair electrons from the 4 valence electrons that it wants to have. We then subtract half of each of the bonds that it has as well, or all the bonding electrons that it has. So here it has 2, 4, 6 bonding electrons. So half of that's going to be 3. So it would be 4 minus 2 minus 3. This is going to be a -1 charge overall for that carbon. But our atom here said it was neutral. So we need to make sure that the oxygen is a +1 charge, so the whole molecule is neutral. Looking at that, we have our oxygen, which has 6 valence electrons. We can subtract from that the 2 electron lone pairs that it has, and then half of the 6 electrons it has. So it also is going to be 6 minus 2 minus 3, so 6 minus 5. It's going to be a +1. This is a total of a neutral charge. So that's good. It matches the charge that we had up here. Last one I'm going to do here is carbon and nitrogen. This creates a, I can't remember it now. It's a common one. I'll remember it in a second, I'm sure. Cyanide, there it is. So carbon has its 4, nitrogen has its 5, and it's a -1 charge. Notice it has that -1 charge, so we have to add one more in there. That's where that carbon gets that extra one there. Bonding then to that, we can connect our lines up. We see it's a triple bond, and each carbon and nitrogen has a lone pair on it. Again, we know from above that this is going to be a -1 charge for the carbon. The nitrogen, however, it likes to have 3 bonds to it and likes to have that lone pair. We saw that over here. So it's actually a neutral charge. It has 5 valence electrons minus the 2 lone pair minus half of the 6 bonding electrons gives it a charge of 0. So that's why we end up with this -1 charge that was listed there. And that's kind of Lewis structures 101. It's really about figuring out how many valence electrons you have and making sure that you put them together, bonding the octet rule. Make sure to put your electrons in the outer atoms first, and then whatever's left over gets put on the inner atoms, and then you make the number of bonds necessary to satisfy your octet rule all the time. So I'm going to talk a little bit about resonance, because there's different structures that atoms can have when they bond together, and the resonance between them is basically them jumping from different isomers that they have, different configurations that they could have. And really the only thing that's changing is these electron bonds, so where that double bond is from one or the other. Starting out with part B, kind of redacted a few of them for time. I don't want to run out of time or spend a lot of time on some of these. But part B is an NO3, so I can draw that out. NOOO bonded together, and we know it's a negatively charged. So when we bond that, and we do our Lewis dot structure, we know that it's 3 times 6, because oxygen is 6 valence electrons, and nitrogen is a 5. So 3 times 6 is going to be 18, plus 5 is going to be 23. Add one more because it's negatively charged, is 24. So now I'd start putting electrons around it. So if I put 6, 6 and 6, we could do that, but notice also that now it's not really, nitrogen doesn't have its octet. So nitrogen is really not happy with this structure. So we need to make sure that nitrogen gets its octet by putting a lone pair on there. And then to do that, we end up having to remove a lone pair from one of these. But now one of the oxygens doesn't quite have its octet either. So what we can do with that is actually create that double bond between there, like that. So now nitrogen has its octet, the oxygen on the left has its octet, and the 2 oxygens down below have their octet. And if we do our formal charge, we'll see that this is going to be a -1, this is a -1, this is 0, and this is a +1. So this whole thing ends up being a -1 charge on there. But the resonance structure that you're going to see is this double bond is, since that nitrogen's bonded to 3 different oxygens, it can jump around and bond to all the different oxygens that are on there. So you'll sometimes see it like that, but then sometimes it'll jump and be like this. Sometimes it'll jump over to the other side as well. So we end up with that resonance structure where it can create that double bond between each of the oxygens, and it goes from one to another, and back. And that distributes that negative charge that we have total amongst all of these oxygens. So all of those get a slightly reduced charge to them. Jumping down to part D on there, for benzene, we can see that we have a ring of carbons. Here it's a 6-membered ring. Each carbon has a hydrogen attached to it, but notice that each carbon is missing its octet. Each one has kind of an extra lone pair sitting on there. And what it needs to do is we need to create some bonds. So we can spread out and disperse alternating double bonds between those carbons to create the benzene ring that we should really have in there. And that makes sure that carbon always has its octet and everyone's happy. But it can also switch and rotate, and we can end up with the same 6-membered ring. I'm going to redraw it here with its hydrogens. Oh, I forgot a bond. And now, instead of being where they were here, we're going to jump over and they're going to alternate. So they really resonate from one to another and back, and so on. And it really just keeps going around in a circle. So really we get this, I'm going to draw it just kind of like this now. We get this resonance of electrons just flowing around that ring structure. We call that an aromatic structure. You'll learn more about that later. But the importance of this is these resonance structures makes the molecule incredibly stable. So the more resonance structures you have, the more stable your molecule becomes, because it's able to distribute any types of negative charges out to it, or across all the different atoms that we have. The last one I have on here is the formate ion. The formate ion it's pretty much as it's shown here, but we can see all now that carbon really wants to have one more bond. Carbon likes to have those 4 bonds, so it needs to create a bond up to one of those oxygens. But it can also resonate over and jump to the right oxygen as well, so it can bounce that negative charge between those 2 oxygens that are there. So if we did a formal charge on this one, we'd see that this is a -1 charge, that's 0, hydrogen 0. So we have that -1 charge. We can redraw this, so now we have this bond kind of going to the right here, and now this is going to have a -1 charge here, where that's 0, that's 0, that's 0. So the total negative charge, or the formal charge on these, is really going to be that -1 divided by 2, because there's 2 different resonance structures that it can have. So this becomes our formal charge for these oxygens. Each one is really a -1/2, because they're sharing that bond between them. There's that resonance structure going between those 2 oxygens, and they're bouncing back and forth at a fast enough rate. It's really hard to kind of isolate it as one, and therefore it's less reactant because it has a smaller charge in there. So now let's go on the formal way to do a formal charge. I talked about it a lot, and we kind of just threw out those numbers. So let's talk about how do we determine that formal charge. So the formal charge, I'm going to say Fc is going to be equal to the number of electrons in the valence shell minus the number of lone pair electrons and I ran out of space, so we're also going to subtract from that half of the number of bonding electrons. And I'm going to do just the first half of these, or not first half, but alternating, just to make sure we can cover everything on here. So the first one on there, part A, is F2CO. So if I draw that out, F, C, and O, I know we can figure out that we need be 7 times 2 plus 4 plus 6. So the fluorines should have 7 electrons bonding to them. The carbons should have 4, and the oxygens should have 6. And I can bond to now and say fluorine bonds to this one, fluorine bonds to this one. Carbon has nowhere else to bond but over here. Fluorine doesn't like to have double bonds, so it almost always just has that single bond to them. It's too electronegative. It keeps its electrons, doesn't like to share. And now we can do our formal charges on these. So here we want to do it on each element of there. So if we look at our carbon first, the carbon has 4 valence electrons in its outer shell, We can see that based off of the group that it's in. It's a group 14, which means it has 4 left. It's 4 in the valence. We can even see one of them is a 2p, one of them is a 2p, one of them is a 2s, one of them is a 2s. So you have 2s2, 2p2. That's where the electron configuration comes in handy. We can subtract from that the number of lone pairs it has. Well, it doesn't have any lone pairs. All of its electrons are tied up in bonds. So that would be a 0. We can subtract from that half of the bonding electrons. So it has 4 bonds. Each of those bonds contain 2 electrons that it's sharing with its neighboring atoms. So that's 8 electrons. Okay, so 4 minus 0 minus half of 8. Half of 8 is 4. 4 minus 4 is 0. We do the same now with oxygen. Oxygen has 6 valence electrons. So oxygen's over here in group 16. That's 16. We subtract 10 from it. We see that it has 6 valence electrons. So that's 6 minus the number of lone pair electrons it has. Well, it has 4 lone pair electrons. And we subtract half of its bonding electrons. So it has 4 bonding electrons as well. So half of 4 is going to be 2. And that's 4 minus 2, or 6 minus 4 minus 2 is equal to 0. So it has a charge, a formal charge of 0 as well. Finally, fluorine. That's going to be 7 because it's a group 17 element, halogen. We're going to subtract from that the number of lone pair electrons it has. It has 6 lone pair electrons. We're going to subtract then half of the 2 bonding electrons that it shares with carbon, and that's going to equal 7 minus 6 is 1 minus half of 2, which is 0. And that's how we can determine the formal charge of these atoms. Doing part C now. Part C is BF4 minus. I shouldn't write it out like that. I should draw it out. BF4. And it's minus. So each of those fluorides is going to want its 7. I already drew these bonds in. I should wait to do that. So each of those fluorides get its 7 valence electrons on there. Takes a while to draw them, so I might repeat myself. And bromine usually has 3, so I can draw 3 of them. Bromine, you can see, or sorry, I'm saying bromine, it's boron. Bromine is Br. Boron usually has 3. It's right there next to carbon, but we have a -1 charge on it, as you can see up here. So we're going to give it an extra electron to play with, and it needs it to make 4 different bonds. Otherwise, bromine couldn't make 3 bonds. And we're going to bond those 1 to each fluoride. And now we have fluorine bonded to our bromine. And doing the formal charge on those, start with the bromine. Bromine has 3 valence electrons, like we just said, because it's in group 13. We're going to subtract from that the lone pair electrons, which is 0, subtracting then half of its bonding electrons, which it has 8 from, and that equals a -1 charge. Fluoride, or fluorine, has a 7, just like we had up above, minus the 6, minus each of those fluorides has 2 bonding electrons. So subtract half of those 2, and that's going to equal 0. So really, these are all 0 charges, and this is a -1. So that -1 charge is going to be on the boron. Part E, which is H2CCH2. That's H2. We kind of drew this up above, or on the previous one, CCH2. So I'm not going to go through all the Lewis structures we had for this one. The carbons bonded to each hydrogen, and we had a double bond between those carbons there. Looking at the formal charge for these, for hydrogen, well, that's easy because it has 1. It's a group 1. it's 1 electron, 1 proton, minus 0 lone pair electrons, subtracting then the 1/2 of the 2 because it has a single bond. It's going to equal 0. Hydrogens are almost always, so it should always be formal charge of 0. Carbons, on the other hand, carbon has 4. We're subtracting from that the 0 lone pairs, and then half of the total bonding electrons it has. Well, it has 1, 2, 3, 4 for the right carbon, 1, 2, 3, 4 for the left carbon. So they're the same. So I can say, oh, and those are 4 bonds. Each bond contains 2. That's an 8. So 4 minus half of 8, which is 4, is 0. So that's how we can do the formal charges for things. If you do have resonance, make sure to take the formal charge for that atom and then divide it by the total number of resonance structures you have that one charge can move around to. And you'll get the same thing. And that's what we were doing back here. We figured out the formal charge of oxygen was -1, but there's 2 different oxygens that it could resonate to. So we divide that by 2. So that's the 2 different resonance structures that it has. For benzene, it didn't really matter because it was a neutrally charged atom. So once it was neutral, dividing it by the different resonance didn't really change anything. This next one, we want to identify the electron pair geometry and the molecular structure. So the electron pair geometry is slightly different than the molecular structure. It's really to show the geometry of the atom itself, or that bond structure that it has on that atom. It has to do with how they hybridize, and that's really talked about in chapter 8. But right now, we're going to talk about the different angles and different shapes that are created from there. I'm going to jump over to a textbook window. There we are. So this is one of the nice tables that they have in your textbook. And this is talking about the electron pair geometry, or the electron pair geometry. So depending on the bonds and the electrons that they have, your electron densities kind of conform to these different shapes. And we can see here in the first column, they have 180 degrees if there's just 2 different distributions of electron density. If there's 3, they're all 120 degrees from each other. If there's 4, they spread out into like a tetrahedral shape is what we call it. And there's 4, and you can see that listed. I can't point with anything. What can I point here? Yeah. You can see that pointed there. Wish I could point on that window. And then when there's 5 different densities, 3 of them spread out in a plane, and then 2 of them shoot up and down. So in that plane, it's kind of like when there's just 3. It's a kind of a planar, like 3 densities all spread out in a planar manner, and then there's 2 more shooting up and down from that. When there's then 6 different electron densities, it shoots out in 4 different directions in that plane, and then up and down from there. And we'll go over those. And we call those linear, trigonal planar, tetrahedral, trigonal bipyramid, or octahedral. I've also heard octahedral called square bipyramid, because that plane creates a square and it creates kind of 2 pyramids going up and down. And I think they have some nice shapes. You can see here it's a trigonal pyramid on the right, and lone pairs or bonds can take up those spaces when you're talking about the electron pair geometries. Now, the difference between electron pair geometry and the molecular shape or molecular structure is that the molecular structure doesn't take into account the electron pairs. We're just looking at those bond angles. And we have a few different names for those. So when there's 1 lone pair in there, what would be trigonal planar is now bent. You can see this in the water molecules, where there's an oxygen with 2 hydrogens down there. They really have some lone pairs up above, 2 different lone pairs. But all we really see out of it is this bent shape. Actually, that would be more of an example of 2 lone pairs with 4 regions, tetrahedral turning into a bent. And there's a lot of different examples, so definitely check out these 2 graphs here and here, and we're going to run through a few different questions here on number 95. So jumping back to my iPad. So this first one, CINO. So that is a tricky one. Oops, I should have been drawing in blue. So really, they're saying that nitrogen is the central atom. So I'm going to start, that's the one we're really focusing on that nitrogen, right? Now bonded to that nitrogen is an iodine, and bonded to that is a carbon, and double bonded to oxygen. There's a double bond there. So really, what's happening here, we can see that oxygen is going to have its 2 lone pairs out there, or 2 sets of lone pairs. Carbon is happy with its octet. Nitrogen has 3 pairs, but it really has a lone pair there as well. And iodine is going to have all the electrons around it. But we really want to focus on what's going on with this nitrogen. What shape is that nitrogen going to be in electron pair geometry and the molecular structure? And we can see that we really have 3 sets of bonds, 1, 2, and then a set of electrons floating out there. And those are all going to want to be as far away from each other as possible because electrons are all negatively charged. So around this nitrogen, they're going to spread out as evenly as possible, creating this about 120-degree angle between them in a plane. So that way they're as far away as possible in the 3 dimensions, and they're sticking into this plane as far away as they can be from each other. So in this case, this is our lone pair. Our iodine can be down here, and even if it's a double bond, it's still carbon. And what happens after that doesn't really matter to the nitrogen. So it's still going to be floating in that 120-degree angle between those bonds, which makes it trigonal planar. And planar means that it's all in a plane. It's actually a flat plane. All the angles are flat on there. And trigonal meaning 3. But what is the molecular shape to that? Well, for the molecular shape, we ignore the lone pairs on there. They're still there. We just don't take them into consideration based on the shape. And we can see that then it creates this kind of bent shape here. So I can say it's supposed to be a bent shape for the molecular geometry, and for the electron pair geometry, it's going to be a trigonal planar shape. I'm going to run through all of these guys. So for part C, we have Cl2CO. So Cl2 means that it's Cl, and it says that carbon is the central atom. That's the one we're really looking at. So then carbon and then oxygen. And these are going to be double bonded, and those chlorines are going to be bonded to that carbon. We can see electron-wise, the oxygen is going to have 2 sets of lone pairs. The chloride is going to have 3 sets of lone pairs. And the carbon has its octet. It's happy. It doesn't have any lone pairs. So just like we had before, we really have 3 bonds going on here, which will need to spread out in that plane as much as possible. So this is going to be also trigonal planar. But in this case, there's no lone pairs on that central atom that we're talking about. Because of that, the molecular geometry is going to be the same as the electron pair geometry. Trigonal planar. There's a there, I think. Part E is SO2F2. So S, that sulfur, is that central atom. And then I'm going to just draw the other ones, F and F next to it. Oxygen and oxygen bonded to that. Oxygen and sulfur, or oxygen always likes to have 2 bonds. And since this is neutral, we can assume that it goes like that. We can check based on our formal charges that oxygen has 2 sets of lone pairs. Fluoride has 3 sets of lone pairs. And then sulfur is a little bit lower in the periodic table. It can have more bonds in there with it. And so it's really happy in that shape as well. It really wants to have, just like oxygen, 6 electrons, or 6 valence electrons, and each of those it's now sharing with another atom around it. So you can see it has 6 bonds total, 2 to each oxygen and 1 to each fluoride. So the shape that it creates, because it basically has 4 bonds bonding to 4 different atoms. Those all want to spread out. We call that tetrahedral. And that's going to be the same as its molecular geometry because, again, there's no lone pairs on that central atom. The last one, ClOF2. That's ClOF2. Oh, what's the central atom? Chloride. So chlorine is the central atom. I'm going to move it a little bit over here. ClOF2. So in this case, just like before, our fluorides get all the electrons around them. They're going to have a bond with chlorine. We know that. Oxygen is going to have a bond with chlorine. Oxygen likes to have 2 bonds if it can, making its formal charge 0. Fluorine is going to have just 1 bond with everything, making its formal charge of 0. Now the chlorine, what's left on there, because chlorine wants to have, it has 7 valence electrons to share. Each one's taken up by one of these bonds. So that's 1, 2, 3, 4. So it has 3 electrons left. Notice also that ClOF2 plus. So that plus charge means it lost one of those electrons. So it really only has 2 more. Someone's got a question for me before you hop off when you're here done. Go ahead and ask the question if you like, and I'll answer it right here if you want. Otherwise, I'll talk to you at the end. So, chlorine has really just 2 more electrons that it needs to deal with, so we can draw those 2 on the end. Oh, right on. Send me, if you're still on the Discords from our physics class, you can send me a link through there, or I'll find you there and I'll add you on the Discord. So as I was saying, chlorine has 2 more electrons that it really needs to deal with because of that +1 charge. Now it has a total of 6 electrons around it, which is going to make it happy for that. But we want to look at what is the shape going to be. So the electron pair geometry has to deal with basically 1 bond to each of these atoms plus those electrons that are there. That's going to make it a tetrahedral shape. The molecular geometry that's going to be there ignores those electrons. They still keep the shape like it was tetrahedral, but we lose one of the legs of it, essentially. That creates kind of this, I'll draw it out here. We have chloride going down and then going back in 2 different directions. These wedges kind of mean they're coming out on my fluorides. And then I have a bond to oxygen. It's hard to draw this. Kind of going out that way. My lone pair would be sitting up on top, but it creates this little pyramid shape kind of going down where the electrons are sitting on top of it. And that's going to be more of a trigonal pyramid. So trigonal meaning 3 and pyramid meaning it forms a little pyramid. It's pretty straightforward. So those are the different molecular geometries and electron pair geometries we had for this problem here. If you have any questions or you run into something you don't know, definitely check out these tables in the textbook here. These are in 7.6, molecular structure and polarity. I just got this off the OpenStax website here. This one here talks about the electron pair geometry, and then there's one a little bit lower that talks more about the molecular geometry as well. You can see some of the shapes that they have in there as well. They have some pretty cool diagrams of things and a lot of explanations and examples. I think this is going to be, this next one's the last one. I got a few more. But this next one is more talking about the polar bonds. So when we talked about electronegativity between those bonds, we can figure out then the polarity of those bonds, kind of which one is which one's polar and which one's not polar. And in more complicated atoms, we have to think about the shape of the atom, not just the two that are pulling apart from each other, because they could be pulling in different directions in three-dimensional space. So in these ones here, we want to look at which one of these are polar and which one are non-polar, and we can do that by drawing out what the shape kind of looks like. And I'm going to keep it kind of simple with my drawings, but we can talk about the shape of them and then what that does to everything. So here, this is H3O+. This is hydronium. It's a very common thing. It's basically your typical acid, where all acids basically break down to. In this case, we have an oxygen with 3 hydrogens attached to it and 1 lone pair. So that 1 lone pair means it's electron pair geometry, or it's got 4 different electron density areas. So that's going to be a tetrahedral shape. And that tetrahedral shape, it's not the same as the molecular structure or their geometry because of that electron pair. So when we ignore that, it's more of a trigonal pyramid. And that trigonal pyramid means that it's going to be a polarized thing, because we have electronegative dipole moment going between those oxygens and hydrogens, pulling down on all 3 of them, or really pulling up toward from the hydrogens up to the oxygen. But the electrons are floating up above and they don't have that same thing. So this ends up being a polar molecule. It creates this polarity between the electron side of it and the hydrogen sides of it. If you really want to see a cool electron density, let's see if I can do this without making it crash. This is a free app. You can pay for it, which I did, and it wasn't worth it. So there's also a free version, but you can see, you can draw out your different shapes. I can clean up the geometry of that a little bit. Oop. Undo that part. And we can see kind of what that shape looks like. We can then calculate its electron density. Let's give it some color for this is the electrostatic potential, and you can see that that red side of it is much more electronegative than this opposite side down here, even though it has 3 hydrogens kind of attached to it. So it creates this dipole moment in there, and we have that polar atom then. We can do the same with part C, do that same kind of structure. The SN is going to be surrounded by 3 chlorides. Chloride is, of course, your group 7 metal. SN is going to be, I can find it here in a second. There it is, group 14. So I have a periodic table on my wall. I should have been looking at this one. Group 14 is 10. So that group 14 means that it basically wants to create 4 bonds similar to carbon, and in this case it only has 3. It's going to end up with 2 lone pair electrons because of this negative charge that's here, just to make sure everything's balanced. These chlorines would have kind of full set. It's octet as there as well. Now looking at the shape of this 10 atom in the middle, we can see that it's going to be tetrahedral, but it's also going to be trigonal planar, or trigonal pyramid, because of that lone pair, which makes it a polar atom as well. The next one, ICl3. This one's a little tricky. We have the I in the middle, and you have 3 Cl's kind of floating around outside of it. Now chlorines there's 6 electrons. Now iodine wants to have 7 electrons kind of floating around it. In this case, it is neutral, so we have to account for all of those. It has 3 bonds right now, so it's really going to have kind of 2 sets of lone pairs off that iodine. And it's not going to be shaped like that, however. really it's going to be more like this. We have the chlorines, and all the electrons, the lone pair electrons, like to kind of float towards one side of it. And it creates this kind of weird T-shape molecular geometry. But we can see when we look at the vectors of the electronegativity that's going on, that we have the chlorines are pulling up, out, and out. So these two are going to cancel each other out because they're just going in opposite directions. But that one chlorine is pulling up where it just has electrons below it. So this is still going to be a polar molecule. I wanted to say atom, but it's not. And this is part E. Part G is SF2. Yeah, SF2. Anytime it's something 2, we can draw it like that, and then we can look at the electrons that it ends up having to see how that affects things. Sulfur, looking at this periodic table, is like oxygen. It has 6 valence electrons. So to account for that here, we need to make sure we have 4 more on the sulfur. The fluorides get all of theirs, because it has a total of 7. So with that bond, we now have everything having a full octet. And we can see that really we're looking at the molecular geometry to determine what it's going to look like in polarity for that shape, which direction those electronegativities are going to pull. This is really a tetrahedral. When we're talking about the electron pair, but it turns into a bent shape for the molecular geometry. That bent shape is going to give it its polarized, the polarity of the molecule itself. It's actually going to look a lot like water does. Water has that oxygen bonded to two hydrogens with 2 sets of lone pairs. Has that same basic shape. It's a tetrahedral electron pair, but it's bent for the molecular geometry. So the next one, this is going to be the last one I think I'm working on, because we've already gone a bit over time. The molecule XCl, X just stands for any element that's out there, has a dipole moment, they're saying, and they want to determine what X could be. And they know it could be either beryllium or sulfur. So we want to know which one of those there are. And the way I would do this is draw out kind of what that molecule looks like and what those electronegativities, those different dipole moments that we have, and we can determine which one it most likely is if both of them have a dipole moment. So beryllium Be is actually in your group 2. Group 2 being here, it's actually this first one right here, meaning that it really only has 2 valence electrons in it. So it's not going to have any lone pairs on this case. So chloride, which does have a bunch of lone pairs, but we don't really care about those lone pairs at this moment. We're looking at the electronegativity. Chloride is much more electronegative. We can see our electronegative. It's really close to fluoride. It's got 3, where beryllium has 1.5. So our dipole is going to be pulling away on both of these. And it's going to be pulling away in an equal and opposite manner because it's going to be a linear atom. This has an angle of 180 degrees, which is linear. So that means that this is not polar. So since it's not polar, it doesn't have that dipole moment in it. So this is not going to be beryllium. It has to be sulfur. And if we look at sulfur, chloride, it's going to pull downwards and away, and it has kind of 2 sets of lone pairs, giving it that bent shape. Because of that, it's going to end up creating a dipole moment, kind of pulling. This is kind of the magnitude of its dipole, is just pointing between those 2 and down. This is going to have a dipole. so it must be sulfur. And that's the last thing I got for you today. Best of luck for everyone who's watching, or anybody who's watching the videos of this. Definitely check back on the old videos. If you are curious and you want to know, I do have a YouTube channel with all of the videos I've created for this site. The link to it is down there at the bottom. You can also just search. Actually, go to my window and do a quick go to YouTube. That's not YouTube. Go to YouTube real quick and search for CH221. You get a bunch of weird videos on there probably. Some of them might even have my face on it. Of course they don't. They did earlier. Put my name in there, Travis. You'll definitely find one, and you can follow those links around to find the playlist I have for this as well. There it is. So use those videos as much as you want. Share them with your friends, anybody who wants to learn chemistry and hear me ramble about a bunch of stuff. Best of luck to everyone on here, and Noah, I'll hit you up on Discord. Enjoy, everyone.